Hello, hello, hello. This is Nicholas, and I'm doing a second attempt at this video because I accidentally turned off my iPad on the first one. So basically, I was just really tired of doing SAT grammar tests, and I said, I just want to do some math for fun. And so that's what I'm going to do today. I'm going to find the area of a circle of radius 1. And you're saying, well, that's not like you to do, Nicholas. I mean, that's just pi times 1 squared or pi, right? Well, yeah, but that's the boring way to do it. So today, I'm going to find the area of a circle using multivariable calculus because I want to kind of showcase some of the deeper mathematics. Now, obviously, you wouldn't actually find the area of a circle using multivariable calculus, although it would be kind of fun. But I want to kind of use that as an excuse to introduce some cool stuff that multivariable calculus has to offer. So to start with, usually I like to relate things back to single variable calc because you're familiar with that. So in single variable calc, if you've got a integral from a to b of f of x dx, then that's the limit as n approaches infinity of sigma I equals 1 to n of f of x sub I times delta x. And so in other words, this is just a Riemann sum. I'm sure you have seen this before. And so if we've got some function, we go from a to b, we have a line segment one-dimensional interval that we're integrating over, right? It's just the line segment from a to b. That's our input space of our function. And then the area that we wish to find is this, and we approximate it using rectangles, right? And so this should be all review. Okay, so now where's the new stuff coming? So now if we've got a double integral, and for now I'm just going to write it over the region R. I'm going to elaborate on that notation a little bit later, but for now just kind of leave it at that, of f of x comma y, and it's f of x comma y because now you've increased one dimension, and so you need to increase by one more functional variable, right? So it's f of xy dA. And it's dA because originally, right, we were just integrating over the x-axis, right, from x equals a to x equals b. Now we need to integrate from x equals a to x equals b, but also from y equals, say, c to y equals d. And so now we've also added a delta y into the mix, right? And so it would make sense that delta x times delta y is delta a. And using calculus notation, right, dx dy is dA. And so that's where the dA kind of comes from, loosely speaking. So this integral as a Riemann sum should make sense, although this is going to look kind of messy. It's going to be the limit as m approaches infinity of the limit as n approaches infinity of the sum from j equals 1 to m of the sum from I equals 1 to n of f of x sub I y sub j, and I'm running out of room, times delta a, or delta x delta y. Right, and that is a kind of scary looking formula, but if you just kind of compare these two, they're really saying the same thing. So this one, it gives you an area under a one-dimensional input space. This one gives you a volume, right? That's why I've added this picture right here. It gives you a volume. It'll give you the volume of what's under this kind of crazy curve here, right? And so that's going to give you all of this volume right here. Okay, and we know that we have to be integrating over a two-dimensional region, right? Because we have two input variables, an x and a y, and then we get out a z. So this right here is our region R, what we're actually integrating over. And then the actual answer to this integral is the volume under the graph itself. And the graph itself is what I'm doing in red right now. So the actual graph lives in 3 space because it has 2 independent variables, just like how this, right, this is y equals f of x, and so it lives in 2 space because it has 1 independent variable and 1 dependent variable. Okay, so this, what I've done in red right here is the actual graph. So I don't know, maybe like a paper kind of folded up. Like yeah, that kind of looks like a paper, I guess. It doesn't really matter. But so the red is the graph, the blue is what we're integrating over, and the black, the whole volume under the red contained within the blue, is the actual answer to our double integral. And that gives a volume under an area, just like how a single integral gave an area under a line segment. So, another thing I kind of want to make a connection to is, let's start with a simple formula. Volume, for a nice geometric solid, nothing crazy like some arbitrary sheet or something, is just going to be area, cross-sectional area times height, right? And area is nothing but volume over height then. But volume is the double integral over the region R of f of x, y, dA, and height is nothing but the functional value at that input, in other words, f of x, y. Now, the whole reason why I introduced the double Riemann sum is to use it at this point right here. See, the double integral is just a sum, and each one of those terms is going to have an f of x, y in it. And so what that allows us to do is, if we treat this like a sum, and each individual term has a f of x, y somewhere in there for each x and y point within R, within our region R, then we can factor that f of x, y out, and we'd have f of x, y times a bunch of other stuff, right? But then we can cancel it with that f of x, y on the denominator. And so in other words, this is actually the double integral over R of 1 dA. In other words, f of x, y over f of x, y. And so what this tells you is that the area of any two-dimensional region R is just that double integral of 1 dA. So the hardest part is actually setting up the bounds for this integral, so we're going to see that later. Thing I kind of want to introduce notation-wise is R. Normally we write it like this. So let me kind of draw some numbers in here. Let's say this is the x value of A. This is the x value of B, and then this is the, right here, the y value of C, and the y value of D. So what we do is we write R as AB cross CD. And this cross right here is not the cross product with two vectors or anything. It's just called the Cartesian product. And the Cartesian product is just a quick and dirty way to say that what you're talking about is this this rectangle who it starts at x equals a and it ends at x equals b, and then on the separate axis it starts at y equals c and y equals d, and then we're including everything in between. So that's the Cartesian product. If we were to write this instead, we could write it as, as the double integral from, say, x equals a to x equals b, y equals c to y equals d of 1. And now you have to write here dy dx. You could write dA, but I mean, you're going to end up using dy and dx eventually at some point. And you have to write, in this particular case, dy dx and not dx dy. That's bad, because notice your first integral, right? If I were to draw brackets, maybe that would help. Your innermost integral is all y stuff. And so it needs to be done with respect to y. And then this is going to give you a number, right? This innermost integral. And then once you get this number, right, this is just a number, you'd have a number, and then it would be the integral from x equals a to x equals b of that number, dx. And so this outermost integral, right, if it's with x's, it needs to be with respect to x. So that's why we need dy dx in this particular case. Now maybe the thought comes into your mind, well, what if I wrote it as the double integral from y equals c to y equals d, from x equals a to x equals b of 1 dx dy? Well, that's perfectly fine. You can totally do that. In fact, this result here is a special case of what's known as Fubini's theorem. And that just says that if you've got a continuous function, right, and so we're kind of looking at this picture and we're assuming continuity, right? This doesn't have any weird gaps or nothing crazy going on. It's a nice function. Then it doesn't matter whether you first sweep your rectangles along the y-axis and then along the x-axis, or whether you sweep your rectangles along the x-axis and then along the y-axis. Either way, you're going to get the same volume. You're just doing it the opposite way, but you're still generating rectangles for the same region. So, what we're going to do now is, let's see. I have Fubini's theorem. I have the area. Now we need to talk about the circle itself. So, we've got a circle of radius 1, x squared plus y squared equals 1. So now we know that a circle, let me see how we started here. Here we're kind of introducing the idea of a double integral, but we're doing it in Cartesian coordinates, right? We're doing it in Cartesian where we have a x from A to B, and we have a y from C to D. Now, you can do an integral of a circle, in Cartesian, but I mean, why would you? So when you see circle, you should immediately think polar, right? Polar is so much better for describing circles, right? Because now this circle just becomes r equals 1 instead of, y is equal to plus or minus the square root of 1 minus x squared. That's kind of yucky. Here in polar, r is equal to 1, right? And that describes that full circle. So now what we need to talk about is double integrals in polar coordinates. Oh boy, I hope that's nothing bad. This online school is exhausting. So double integrals in polar coordinates. And so to start off with, remember before I was talking about in Cartesian coordinates, this dx dy business, right here, dx dy being dA. So it might be tempting to just, in polar, right, we take a coordinate x, y, and it goes to r theta. So it might be tempting to just say that dx dy is equal to dr d theta, right? That is wrong. Don't do that. I will show you why. Basically, what happens is when you switch from one coordinate system to another, you need to take into account how any arbitrary region in space changes as a result of that coordinate system change. So let me detail that a little bit more. So let's say we still have this circle. And so in Cartesian coordinates, right, we would be talking about some infinitesimal, I'm being very loose in my description here, some, quote, infinitesimal square, right? And so it would have a base of dx, and a height of dy. And so then its area is dx dy, and that's where the dA comes from. Now, in polar coordinates, it's different. Let me see if I can thin my pencil, because I'm going to be writing pretty small here. So in polar coordinates, right, now we're talking about a thin sector of a circle, right? An infinitesimal, sector of this circle. And so now, instead of going a little x nudge and going a little y nudge, we're going a little theta nudge, a little d theta, right? So now we have this little square and or this little sector, and so now we're going to be talking about, if we're to imagine, we're still talking about a small region here. We're going to talk about this subsector right here. And I'm just picking this arbitrarily. I mean, I could have drawn the subsector here or something like that. In other words, it just aligns with this bigger sector, right? This is a very non-rigorous way to derive, well, I haven't introduced it to derive the correction factor, I guess you could say, for how space changes when you convert to polar. So if we talk about this minuscule infinitesimal part of the sector of this infinitesimal sector, we're talking about an infinitesimal part of this infinitesimal sector, right? Then as this d theta gets smaller and smaller, right? This part right here of the sector is going to become a rectangle, right? It's going to get closer and closer to a rectangle. And so basically what we're interested in is that rectangle's area, right? And so when we find that rectangle's area, that would tell us what dx dy would need to be equal to. Because remember, in just plain old Cartesian, it was just that just gave you a rectangle, right, with a base of dx and a height of dy, and so its area was dx dy. And so now we're just going to need to find the area of this, and that's pretty easy. So basically, what it comes down to is that this little arc right here, which very closely approximates a rectangle for smaller and smaller d theta. This arc has a length of r d theta, right? Because if you remember from this is just kind of basic geometry, s is equal to r theta. Well, what's r theta? Well, theta in this case is the d theta. So it's r d theta. Okay. And then the this part right, oh no. This part right here is just a tiny nudge in the radius, right? A tiny dr, right? We go from r, do it in blue. We go from r to r plus something a little extra, and then we're calling that dr. So then this red kind of hunk of this sector, which becomes closer and closer to a rectangle, is going to eventually become a rectangle, and that's going to have an area of the base times the height. In other words, r dr d theta. And this is actually what dy dx is equal to. It's r dr d theta. It's not just dr d theta. It's r dr d theta. And you can kind of remember it like a pirate. That's how I remember r dr. But anyway, so that's kind of a non-rigorous way on how to derive that. But basically, the whole point of that discussion was so that whenever you convert to polar, you need to multiply by an extra factor of r. And that can either be very beneficial at times or very detrimental at times, depending on what you're trying to actually integrate. It can make the difference, or it can just totally destroy you. So now that we have that dx dy. Oh, now I need to change my, it was so thick. There we go. Okay, now that we have that dx dy is r dr d theta, you, in a non-rigorous sense, you know, why not rigorify it? So the way that we're going to rigorify it is we're going to use what's called the Jacobian Matrix, and this is a far more generalized version for when you are doing a change of variables, what you need to multiply by. In other words, what your correction factor is going to be, right? R in this case is our correction factor, so that our area is being translated correctly from one coordinate system to the other. So the Jacobian matrix is basically just a big glob of partial derivatives everywhere. So in the polar coordinates, we have the transformation x is equal to r cosine theta and y is equal to r sine theta. So in this case, the Jacobian matrix for this 2x2 transformation, it would be a 2x2 matrix because we've got two variables that we're going from to two variables that we're going to, right? We're going from x and y to r and theta. So the Jacobian matrix then is basically a matrix of all possible partial derivatives between x, y, r, and theta. So it's the we would have partial x with respect to r, partial y with respect to r, partial x with respect to theta, and partial y with respect to theta. And so now when we actually take those partial derivatives, partial x with respect to r, that's cosine theta, because r is the variable, theta is the constant. Partial y with respect to r is sine theta. Partial x with respect to theta is negative r sine theta, because r is the constant. Cosine theta is what's varying. The derivative of cosine is negative sine. Partial y with respect to theta is r cosine theta, for the same reason the derivative of sine is cosine. Now the determinant of this matrix is r cosine squared theta minus negative or positive r sine squared theta. And that is just r. And so that's another way to think about where this r comes from. It comes from the Jacobian matrix, which I have two videos deriving, you know, where this comes from and why it's useful. So I'm not going to derive it in this video too. You could watch one of the other two for that one. But either way, the motive, the moral, not the motive, the moral of this story is multiplied by the r in polar coordinates when you switch to polar. So what does this look like? If you've got a double integral, say from a, b, c, d of f of x, y, dy, dx, then that's the same thing as a double integral, and it's still going to be f of x, y, or I'm sorry, x is r cosine theta, and y is r sine theta. And then dy dx is r dr d theta. And so you always write it in that order, r dr d theta. And so what that means is that, if you put brackets here to kind of help you, your innermost integral is going from r equals, say, a to r equals b. And then your outermost integral is going to have thetas, from theta equals c to theta equals d. And those are going to be in radians. Always use radians in calculus. So now let's actually get to the problem of finding the area of the circle. So in polar coordinates, basically we need to ask ourselves, how would we write that region, a circle of radius 1 in polar coordinates, right? Well, theta, which is just this angle from the positive x-axis, it goes all the way around. It needs to make a full circle. And so theta goes from 0 to 2 pi. Right? Because if it didn't, right, say if it only went from 0 to pi, then we would only get half the circle. And if it only went from pi to 2 pi, we would only get the other half. So it needs to go from 0 to 2 pi to get the whole thing. And now it's a circle of radius 1. So r is 1. That's the beauty of polar, right? Now we don't have an x squared plus y squared equals 1. It's just r equals 1. So what if we were looking for the area of a circle in polar coordinates, the area is equal to the double integral over our region of 1 dA originally. In polar, that's the double integral still over the same region of 1 r dr d theta. And now our region can be rewritten as r is going from 0 to 1. In other words, the radius of the circle, right? We start at 0 because if you go and start at 0 and then you go all the way up to 1, you're going to get that circle of radius 1. And then theta is going from 0 to 2 pi because we need to sweep out the whole circle. And it's just 1 r dr d theta, which I'm just going to write as r dr. And then I'm going to put brackets to kind of help us here, d theta. And now this is just a straightforward evaluation. Get the integral from 0 to 2 pi of, now we are just going to evaluate that, and it's going to give us a number, right? So the integral of r dr, that's r squared over 2. So we got r squared over 2, evaluated from 0 to 1, d theta, which is equal to the integral from 0 to 2 pi of just 1/2 d theta, which is 1/2 times 2 pi, or pi, just like we wanted. So you can actually find the area of a circle using multivariable calculus and polar coordinates. And of course it's going to be pi, right? It's just pi r squared. It was pi to begin with. But, so why did I go through all this? Well, okay, you never would actually use this method to find the area of a circle. But this was kind of just a fun video to do, and you can use this method to find the area of more complicated shapes, right? In fact, any shape where you can, if you want to write it in polar, any shape where you can easily describe it, right? Finding the bounds is usually the hardest part, where we put these bounds in right there. So if you can do the bounds nicely in polar, then you can calculate the area of that shape. So it's kind of an easy way to calculate an area without much geometric ins and outs type knowledge, right? If you were finding, say, a torus, right? I did a video on parameterizing a torus. If you wanted to find the volume of that torus, that would be very hard to do. I don't even know if it's possible geometrically, but with calculus, it's possible. Or on one of our tests in Mr. Mack's class, we had to find the volume of the solid that was created by the intersection of two cylinders. And that is very hard to visualize, what the intersection of those two cylinders, what kind of shape that would create. But with calculus, you can do it very quickly and kind of without much thought. So I hope you got kind of a laugh out of this video, but I hope it was helpful too. So with that,